Moving on to chapter 5, the first thing we're going to talk about is the derivatives of exponential functions. Then we're going to get into derivatives of trigonometric functions. Not too difficult. All right, so the first thing we're going to talk about is actually y equals e to the x, because you've probably seen this before, but you have no idea what this is. So I'll give you a quick explanation of e to the x. First of all, the letter E. E represents Euler's number. Okay, he was a mathematician. It's pronounced Euler. And this is just another symbol to represent an irrational number. Okay, an irrational number, one that you're probably very familiar with, is pi. So there's no other way to represent pi because it is irrational. And irrational means there's no way that I can form a fraction with it or a ratio. There's no possible way I can form pi using two integers on top of each other. Okay, same with Euler's number. There's no way that I can represent this number, so we give it a letter and we're off to the races. Okay, what's the value? Just like that's approximately 3.14. This one's approximately 2.718. Okay, it doesn't really matter. We like to use e just like we like to use pi. Another way we can say this is a natural number, or the natural number. Okay, Euler's number. Now, get a little recall in here for logarithmic functions. So let's recall the inverse of b equals x to the y is y equals log base times x. Okay, so just remember this from advanced functions, how we go from an exponential function to a logarithmic function using the inverse. Okay, now, if we do the same thing with Euler's number, the inverse of y equals e to the x is, use the same strategy, log base e to the x. Now, this right here is special in math. Okay, we call this the natural logarithm, or ln x. Okay, I know you've seen ln, you have no idea what it is. This is just a logarithm with e as a base, with Euler's number as a base. So if you ever see this, this is what it means. Okay, Euler's number. Now, the derivative of this function, or just an exponential function in this case, of y equals e to the x, amazingly, is e to the x. Okay, so a few examples of finding the derivative using exponential function, this natural number that we've discovered, Euler's number. It's going to be the same idea, except every time you have e to the x, the derivative is just e to the x. So for instance, when I have y equals e to the 3x, consider this like e to the x. So the derivative of this is just e to the 3x, except you have to remember chain rule. Every time you are finding the derivative, I have to find that chain rule up here. So I'm multiplying this by 3. This is y prime. So y prime is 3 e to the 3x. Done. Okay, next, same idea. Now we have a binomial up in the exponent. G prime at x is just this function times the derivative of that up there. Okay, and this is done. I can expand this. No, actually I won't. Just keep it like that. Okay, so g prime at x is just the function times the derivative in that exponent. Okay, it's very, very common. You're going to be doing that. You're going to have e to an exponent. Just write down the question basically and find the derivative of that exponent. Okay, next. Here I have a multiplication, right? So far I've just had a monomial technically, right? Had a binomial in the exponent, but it's just a monomial, pretty straightforward. Now I'm going to start having product rule, quotient rule, whatever the case may be. So here is just the derivative of the first term times the second, plus the derivative of the second term times the first. Okay, and now I have an e to the x in both of these terms. This is one term, this is another term. So I'm going to factor out that e to the x because that's what I do in math. Okay, 2x plus x squared, close brackets, and this is my derivative. Okay, so in this example, we have to determine the equation of the line tangent to this function where x equals 2. Okay, so again, the equation of the line, not just the slope of the tangent, not just the first derivative. But in order to find the equation of a line, I need slope. I need this slope of the tangent, so I'm going to find y prime. Okay, and this is quotient rule, but I'm going to go ahead and change this to product rule because I can. And now I'm going to use product rule. The derivative of this times this plus the derivative of this times that. And now I'm just going to convert everything into positive exponents. So I'm going to leave this negative 2 up here. This x3 comes under here. The e to the x is on top of that term. And here I just have an e to the x on top and an x squared at the bottom. Now I'm going to add these two and come up with one term. So this guy needs an x. Negative 2 e to the x plus x ex all over x3. Okay, so I found the common denominator x cubed, multiplied this by x over x, and I'm left with this. I have an e to the x over here again, like the previous example, that I can factor out. So my final y prime is e to the x negative 2 plus x over x3. Okay, so at x equals negative 2, if I want to plug in negative 2 into this first derivative, what are we going to get? Well, I look right here, and I know I'm going to get 0 right away. Negative 2 plus 2 is 0, times e to the x is 0, 0 divided by x cubed, 0. So at this point, the slope of the tangent is 0. So if I'm doing y equals mx plus b, and my slope is 0, I know that I just have a horizontal line at y equals b. So how do I find that value of b? Very easy. Plug in 2 into your original function. Y equals e to the 2 over 4. And this is actually the equation of that tangent. What is e squared divided by 4? Well, if you put it in your calculator and you use Euler's number, your calculator has the e, but if you convert it to Euler's number, it's going to be approximately 1.847. Right? So this is my graph. This is 1, this is 2. At 1.847, I have a horizontal line. That's supposed to be horizontal, by the way. It's a little tilted.